quantum chemistry meets quantum computing. Exciting, right? So let me just start off with a very brief introduction to maybe cater to the audience who are not that technically sound. Quantum chemistry is a field that has been around for many, many years, right? It deals with the quantum stuff. And by quantum stuff, I basically means the very, very small particles of a particular material. So trivially, we can say that how the electrons behave with each other or maybe with their surrounding neighborhood. That is what quantum chemistry is all about. And we have been studying this field for a lot of time, but using classical computing techniques. But with the advent of quantum computing, which is like a new paradigm of quantum computer science, we are exploring new areas of research that have exponential growth over time. So we are discussing a lot of exciting stuff today. What is quantum computing, you might ask? It is a field of computer science that uses the principle of quantum mechanics to perform calculations and operations. But unlike classical computers, which you might already be very familiar with, which use bits and they can be only in one of the two states, 0 and 1, quantum computers use qubits. And that can take various advantages of various phenomena, which are more quantum in nature, like let's say superposition or entanglement, and much, much more. And that is why this is important, because quantum computers hold the potential to solve some of the most pressing issues we have today that are intractable for classical computers. And quantum computing, however sci-fi like it might sound, it's not just a dream today, it's very, very real. The quantum tech ecosystem is progressing at a rapid pace, and the accelerating advances we are seeing in quantum computing are serving as a powerful reminder that technology is rapidly advancing, and that too towards commercial viability. To give you a few examples, in just the past few months, we had researchers at DARPA release a very comprehensive report on quantum resource estimation, a very fundamental thing you might want to read about. Atom Computing, a pioneer startup in the space, released their first 1,000-qubit machine, a landmark in the hardware ecosystem, which was very quickly followed by a new quantum roadmap being released by IBM. And then there was this team from MIT successfully scaling the fault-tolerant algorithms to maybe a whole new level. All these examples are just a testament to how these breakthroughs are accelerating and the investment dollars are pouring in. Quantum computing startups are proliferating, all with the aim of providing tangible advantages in domains like optimization, finance, machine learning, and much more. It's safe to say today that whatever industry you are a part of today, you are sure to see the impact of quantum on your industry in a very significant manner in the days to come. Of these various industrial applications that you see on the screen, one which I'm really, my personal favorite is the chemical industry, because this is poised to be one of the early beneficiaries of computational capabilities that quantum computing might offer. And companies must act right now to reap the benefits of this particular technology in the near future. But why do I say so? Because honestly speaking, it has a very direct impact on the computer-aided drug design methodology. Quantum computers' capabilities could make it possible to significantly improve our understanding of how systems are governed by quantum mechanics, such as molecular structures or chemical reactions, the processes involved within, all at the core of this business of chemical industry. The intersection of quantum chemistry and quantum computers is poised to revolutionize the diagnosis and treatment of diseases. And such a revolution, believe me, is likely to increase the pace, the precision of disease identification, detection, drug design, pharmaceutical discovery, genomic analysis, and whatnot, maybe even customized medicines and interventions. So all that is very exciting, but for a minute, let me just dive a bit deep into this problem to try and convey the message to you in a more statistical manner. Today, we need billions of dollars spanning over decades of time to bring just one potential drug to the market. Pause a minute and let that sink in, because this is huge. So this is primarily because how complex the entire drug design process is. To explain this a bit further, to develop a new engineered material or maybe a chemical compound, researchers typically evaluate thousands of chemical reactions and molecular interactions. On top of that, we need to assess the potential drug reactions, the side effects on so many individual human systems. And at the same point of time, especially today, we also need to consider the environmental risk associated with it, because obviously we all need to go green. And all this, again, just to get only one new drug in the market. But the interesting thing over here is that quantum computing could change that. It's expected to have an outsized impact on all of the aspects of this discovery phase. And this includes genetically, maybe scientifically valid evidence pinpointing to, let's say, the biological origins of a particular disease, or safely manipulated therapeutic benefits of a particular drug. And quantum computing could potentially also identify compounds for these actions that could serve, let's say, as a starting point to improve the strength and the precision of the compound. All this ultimately helping reduce the time and the cost of bringing life-saving drugs to the market, which is really, really important. But there's a caveat to this. At the moment, unfortunately, even the world's highest performing quantum computers don't yet have enough computing power to compete with the classical machines. And this is me honestly stating that we don't need to hype this as much, but at the same point of time, we need to be very practical with the use cases. Some applications I mentioned before might require tens and thousands of qubits, which isn't practically achievable just yet. But the good news over here is that, especially for the pharmaceutical industries that rely on quantum industry, or maybe the quantum chemistry aspect of it, only about 1,000 logical qubits, and we are kind of set to simulate materials and molecules. And that landmark we have already achieved, like just achieved, right? We have now 1,000 qubit machines available. So with the quantum rat race in high gear, the ability to realistically simulate complex molecules is rapidly progressing. Within the next 5 to 10 years, as quantum computers become more and more powerful, which I'm sure they will become with the pace they are growing at, the ability to simulate the structures and behaviors of complex molecules and materials is expected to dramatically improve. And hence, companies must start building at least the research-oriented project showcases today, in order to kickstart their quantum journeys and potentially reap benefits in the years to come. But all this is not that easy as it sounds. It is very easy to preach that everyone should start exploring quantum computing, but to actually make an impact, we need to have a very strong foundational and fundamental base to start with. We need to have a quantum workforce ready to take on the challenges head on and guide us into the future. Womanium understands this. And as a nonprofit organization, Womanium, based out of Washington, D.C., our goal is to create the scientific leaders of tomorrow. We take young, enthusiastic people, both men and women, and train them on technologies that are 10, 20 years in the future. And we have been doing this successfully for a variety of technologies over the past several years. Right now, it's quantum. And as part of the Womanium Quantum Training Program, hosted annually during the summers, we have successfully trained over 4,000 participants on quantum technologies that not only includes quantum computing, but beyond that, we are touching upon quantum sensing, quantum materials, quantum communication, and much more. Our program success is evident from the fact that over 40 companies have actually hired from our program's participants. Not only that, many of our participants have actually gone forward and explored their entrepreneurship skills. We currently have 3 quantum startups in formation. Interesting, right? And all while ensuring a diverse participation in our program with a consistent 44% female participation being observed. This entire success of a program is largely because of our invaluable contributions coming in from our amazing, amazing partners. We work with almost every leading quantum company today, including Xanadu, whom we have with us today. Thank you, Xanadu, but also with some of the other leading national labs, premier research institutes, and many others. All this looks great, right? But to truly create an impact and contribute towards the scientific domain, we need to work on real-world problems. To make that possible, we took a step ahead from our training program and created a new set of a program called as QSL, or that stands for the Quantum Solutions Launchpad. We bring in the top performers from our Womanium program, train them, mentor them on very specific industry relevant skills, and then provide them with the opportunity to work on real world problems with our industry partners. And bringing in people with different skill sets, different expertise, different backgrounds to join forces with our industrial partners, we have helped our partners fast track their progress in many instances. Working with the Naval Nuclear Lab, for example, we have explored and contributed to domains like quantum sensing and quantum computing simulations for nuclear propulsion, CFD, engineering simulations, which is state-of-the-art work, and none of the other organizations are doing that. With companies like Pramatra, our work revolves around an exciting prospect of establishing space-based QPD systems for satellite communication. The topic itself is that exciting. And this list goes way beyond the partner shown on the screen right now. One such partner is here with us today, Xanadu, one of the leading quantum computing companies from Canada with whom we have worked on a very exciting problem. As part of the Womanium Quantum Solutions Launchpad, we aimed at improving the quantum chemical simulations done today. And before we jump on to the next part of the presentation, where Dr. Mojde we have with us today will be diving deep into the technical work we have accomplished, let me try to give a brief overview of what the project is all about. We are insightful of the large or maybe high-level goals of actually creating an impact in the society. We want to create an impact by improving battery chemistry, by making efficient drug design possible, and many other applications. But that won't happen on its own. Quantum computing is not like a magic wand which you wave and stuff happens on its own. We need to be practical about it. We need to make sure that we don't go ahead ourselves in all the quantum computing hype. So to make that happen, we need to map a whole lot of quantum information onto qubits, process it, analyze it using quantum circuits. That is it, right? Um, but unfortunately, there are a lot of issues which come into the picture once we start implementing this stuff in real life. Nothing is as easy as it seems. High circuit depths, large number of qubit counts, and many other difficulties are something which we need to face. And to solve all these issues, we work towards and actually work towards solving practical problems. We need to put in a tad bit more effort. With Xanadu, as part of the Quantum Solutions Launchpad, we looked under the hood of all these quantum chemistry algorithms. We realized that it was absolutely essential to understand the math and the algorithm structure that sits beneath these applications. And this is where all the current work exists. We try to optimize something called as the LCU decompositions to reduce the overall cost of the quantum circuits. And what is LCU, or maybe you might want to learn what LCU means, or what is it we actually achieved. We shall move on to the next part of the presentation. So we had amazing researchers coming in from the University of Montreal, IQC, and the University of Boston, namely Dr. Mojde and Dr. Prashant, who worked as part of the Quantum Solutions Launchpad from Womanium in collaboration with Xanadu to work on this very problem. And today, for this particular webinar, we have Dr. Mojde with us to talk in depth about the project she accomplished and shed some light on the importance of the significant results she has achieved as a part of this entire collaboration effort. Yeah, so Dr. Mojde, the stage is yours. Please take it away.
Thank you, Vardaan, for the introduction and great information. I'm sharing my screen. Let me know if it works. Perfect. Okay. Hello, everybody. Good morning, good afternoon, good evening. Welcome to this talk. In the continuum of Vardaan's insightful talk, I'm excited to dig into more details of using quantum computers in quantum chemistry, especially in quantum chemical computations. Quantum chemical computations on classical computers, as Vardaan mentioned, achieved a huge success in the last decades due to both progress in computer technology and in development of quantum chemical methods. But we have some important buts in this talk. But the situation is still far from the ideal, and scientists face challenges in using classical computers. Today, I'm going to show you what these challenges are and how we can solve them. The first issue that scientists face is exponential scaling of the problem. Let's see what it means. Our goal in quantum chemistry is investigating the different structures and systems and interpret their properties. And the first step to do this is writing the Hamiltonian of the system. Imagine you have a system with just one electron and you want to write its wave function. To do that, you need 2 to the power of 1 complex number, and the wave function can be written like this. Now I'm giving you one more electron. For 2 electrons, the number of possibilities to distribute them among the orbitals will be 2 to the power of 2 with this form of the wave function. Now you can guess for 3 electrons, there are 2 to the power of 3 or 8 complex number or possibilities to distribute electrons. These are very small number for the structures, this number of electrons, I mean. In many-body problem, to describe a system, we deal with large number of electrons. So writing a Hamiltonian of a system with large number of electrons will be complicated, time-consuming, and need high computational cost. For example, let's consider this system. This is a structure with 40 electrons. To investigate this system, we have 2 to the power of 40 terms in the wave function of the structures, or there are this number of possibilities to distribute electrons, which is a very huge number. Then, now we can guess, we can realize what was that exponential scaling problem means. Yes, the cost of finding the exact properties of a system grows exponentially with the number of electrons or with the size of the system. Now, the question is that how we can find a solution for this challenge. The first solution is applying approximations. Actually, this challenge motivated scientists to develop numerical methods and applying approximation in their calculations instead of finding exact solution. But they still need computer power to simulate large systems. Then even applying approximation does not work well. And we have to think about new ways, which one of these ways can be using a quantum computer. Yes, now we are going to use quantum computers in our studies to investigate different structures. Let's see, let's check everything. As I mentioned earlier, in the first step in investigating a system is writing its Hamiltonian. For those of you who may not familiar with, Hamiltonian is a set of data or information about the system. Actually, it's a mathematical description of a total energy of the system. We can find a way to write the Hamiltonian to use in classical computers, but how it would be if we want to use quantum computers to describe our system, to investigate the system. Can we use the same Hamiltonian or do we have to change it? Let's see. The Hamiltonian in quantum model for electronic system can be written in second quantized form or by using creation and annihilation operators, as we can see here. But fermionic operations are not fundamental operators in quantum computers. What does it mean? It means that this quantum computer is not able to understand what this information, what these fermionic relations, and it doesn't able to understand what is happening here. So we have to map this Hamiltonian into qubit Hamiltonian. That could be a Hamiltonian which is written as a linear combination of unitaries, or in short, LCU. In summary, we have a second quantized form of the Hamiltonian, and we want to change its format and map it to a qubit Hamiltonian. To do that, there are different mapping techniques. Actually, they are all used to map fermionic system to qubit system. Each have the advantage and disadvantage, and the choice of mapping may depend on the specific problem being addressed. One of the most known of that mapping methods is Jordan-Wigner mapping, which is developed in 1930s. This method is more popular in the context of simulation fermionic system. Using this relation, we can change the Hamiltonian, which is described in fermionic, to qubit or spin Hamiltonian. And it gives us a Hamiltonian which is written in linear combination unitaries, as we can see here. So now we realize how to achieve the form of the Hamiltonian, which is needed to use in quantum computers. However, we still have to consider more and try to reduce the cost of the calculations and figure out which LCU is better. Actually, the idea of computational reduction is the heart of computational problem. We should think how we can reduce the general measurement requirements, circuit depths, number of gates, or in general computational time in our calculation. There's a factor called one norm, which we can see here, that gives us an approximation about these cases. It's sum of the absolute values of the absolute value of the coefficient. One norm is related to the complexity of Hamiltonian operator. Then reducing the one norm leads to reduction of the computational cost. Then our goal is to investigate the difference method to see how we can reduce the one norm, which leads to reduction of the computational cost. Different work have been done on one norm, giving insight about its importance and studying various methods to reduce its value. In our work, we use these four techniques, which are fermionic-based LCUs and two advanced methods. The first method that we use, or the easiest LCU, is a linear combination of Pauli products, because Pauli products are unitary by themselves. So just by by doing Jordan-Wigner mapping, we can have this form of the Hamiltonian, this linear combination of unitaries. We mentioned that to use a quantum computer, we need to write the Hamiltonian in a format of linear combination of unitaries. Just by doing Jordan-Wigner mapping, we have Pauli products here, and it's the easiest way to change the Hamiltonian. The summation goes over the total number of Pauli products. One norm of LCU decompositions is defined here. We calculate the one norm for this one norm in this method for these 5 structures. These are all light structures and have many industrial applications. Actually, we calculate the one norm, but as I said, we have to compare one norm with a difference method to see which one gives us lower value and gives us lowest computational cost. To do that, we could improve the results by grouping Pauli products. Actually, if we do just an arbitrary grouping, we may lose the properties that group will be unitary operators. But if we satisfy certain relations like anti-commuting Pauli products with the coefficient, we will be able to earn unitaries that reduces the one norm. This method is called anti-commuting Pauli products. Here we compare the one norm for these two methods, Pauli products and anti-commuting Pauli products, and comparing them say us that one norm of anti-commuting is always lower or equal to the original one norm. We investigated this matter with our structures, with the same structure that we calculate their one norm with Pauli products. We can see that one norm of all of them has decreased. Then using anti-commuting Pauli products gives reduction in one norm and computational cost. But we are looking for better results. It is important to know that there is a lowest value for one norm, and that value is the half of spectral range of the Hamiltonian. It means no matter which unitaries we want to use in describing the Hamiltonian, in writing the Hamiltonian, we are not able to reduce one norm to the lower value of delta E over 2 or half of delta E. Then we need to look for another solution, and that solution can be changing the Hamiltonian. We can change the Hamiltonian, and when we change the Hamiltonian, delta E will be changed, and we can reduce the one norm. We investigated this method as well. One way to change the Hamiltonian is to use symmetry function. The idea here is decompose the difference between the Hamiltonian and a symmetry operator rather than the Hamiltonian alone. Actually, in the same way that as we subtract constant or identity operator from the Hamiltonian, we can subtract all symmetry operators. We use this strategy, and instead of using Hamiltonian, we apply H minus S in our calculations. S can be built by an arbitrary function, and in our calculations, we choose number of electrons. We applied this method. Actually, we combine symmetry shift method with fermionic methods, with Pauli products and anti-commuting Pauli products, and we can see the results here. The results was wonderful. We saw reduction of 50% in average for these structures, which is a huge achievement. But we continue, we tried another method. Actually, another way to change the Hamiltonian and change the spectrum is using interaction picture. In this method, we try to subtract from the Hamiltonian a part that is possible to simulate. Then we can divide the Hamiltonian into two components, H0, which is a solvable part, and HR, which is a residual part. So the idea here is that the linear combination unitaries is only needed for the differences between H and H0, or for residual part. And the goal is to achieve the splitting such that the norm of H0 is much greater than norm of HR. We chose H0, and again, we calculated one norm for our structures. We combined the interaction picture. Again, we combined the interaction picture with fermionic methods using both Pauli product and anti-commuting Pauli products. And here the result was great. A great reduction for one norm up to 90% was achieved. Yeah. In summary, we present different techniques to reduce one norm of different structure. Here we can observe a graph shows results for the calculations of one norm for molecular Hamiltonian using different LCU decomposition. As we can see, the greatest one norm reduction is observed for interaction picture combined with anti-commuting Pauli products. Besides these great results, we already started other steps. We are trying to test complex molecule by using this method. We also continue working on reduction of one norm to have even better results and to reduce the cost of the calculations. Thank you everyone for attending this webinar. I hope you enjoy it and learn something new.
Okay, yeah, thank you everyone. Before ending the call, maybe one last question to, let's say, the Xanadu team. Catalina had been a huge support throughout the journey. So Catalina, how was your experience working with Mojde and working with the Womanium team throughout the course of the QSL project?
Good, thank you. Thank you for organizing the Quantum Solutions Launchpad. As you can see, we had a lot of questions. This is a topic that is interesting for us. So thank you, Mojde, for diving deep and explaining it to us. In general, it's very useful for us to, learn. We're always learning new things and exploring, the boundaries of what we know. So I would also like to get maybe some insight, Mojde, if you can say a couple of words of if you had any recommendations for people continuing this work, something that you learned as part of the process, maybe any particular tips that you can give to people who are working on this. This is useful for us and probably for everybody else on the call.
Yes, thank you. Actually, for this specific problem, maybe exploring alternative quantum algorithm or hybrid methods and collaborating with expertise who work in this field or contributing open sources project related to quantum chemistry or other fields. And communication as well, doing communication with expertise. And I think all these factors are accessible through the supportive environment of environment provided by Womanium.
Glad to hear that. Before ending the call, I must say very warm regards to the entire team responsible for the particular project. So great job, Mojde, Prashant. It was a pleasure working with both of you from the Womanium team. These are some of the fellows who worked on this particular project from the Womanium end. But not only this, we had people coming in from Xanadu in collaboration. So huge support from Catalina and Utkarsh, who played a great role in the success of this particular project. Thank you once again. And finally, acknowledgments to the Womanium team who were working at the back end of things, supporting everyone involved in the team and making the success of this project possible. So thank you again for the entire Womanium team for making this happen.